Hello, everybody, and welcome to this event organized by GoLab. We are very happy you could join us. GoLab is a series of events dedicated to Go, the open source programming language developed by Google. It's a simple, efficient, and fast language. GoLab is organized by Develer, a company that develops hardware and software with industrial applications, with a great focus on emerging and open source technologies. At Develer, we strongly believe in supporting training and collaboration, and because of this, we regularly organize technology events like conferences, workshops, courses, webinars dedicated to state-of-the-art technologies such as Go. Before the beginning of the talk, I have a few announcements. If you experience problems with your connection, or the streaming stops for any reason, the thing to do is go back to the confirmation email and click on the Join button again. This will bring you back to the live room. At the end of the talk, we will have a Q&A session with a dedicated Q&A chat, different from the main chat. So we kindly ask you to wait and save all your questions for that special Q&A chat. Finally, please join your Discord channel to network and share ideas. You can click on this link above us to join us there. Today's speaker is Paolo Galeone, who will share his insights in a talk about train and deploy TensorFlow models in Go. So welcome, Paolo. We are very happy to have you here. Hello.
Hi, Laura, and thank you very much for your introduction.
So I will leave the stage to Paolo. Enjoy the talk and stay tuned for the Q&A session at the end.
Okay, so thank you everyone for joining this talk, and I'm really happy to be here sharing my little bit of knowledge about how to train and deploy TensorFlow models in Go. So I hope you enjoyed the talk, and I hope to receive some good question at the end of the talk. So thank you and enjoy.
Hello everyone. I am Paolo Galeone, and today I'm going to talk to you about how to train and deploy TensorFlow models using Go. But first, let me introduce myself. So I am a computer engineer. I'm also a long-term gopher. I think I am one of the early adopters of this language. And I maintain several repositories that use Go as a main language. The most famous repository I maintain is the so-called tfgo, that is a wrapper around the Go bindings of TensorFlow that simplify the usage of TensorFlow itself, because the bindings are not so easy to use. We will see this later on in the talk. Moreover, I'm also the tech lead and the leader of the machine learning team at Zurotech Italy. And moreover, I am a machine learning Google developer expert. Google developer expert is just a person with expertise in a specific area of Google technology, and in my case, it's TensorFlow. So I guess I spent already too many words about myself, so we can move on and start. Okay. So this is the simplified machine learning workflow. So in practice, what happens in some industries and also on dedicated devices? We have 5 simple steps. The first one, and perhaps the most easiest, is the data gathering. So we have to gather all the data that we need. This is something that we won't cover inside this talk. But however, data is of course required to train every machine learning model. Then the second step that is often something useful to do is the data cleaning. So we have to look at our data using some data visualization technique and also do some cleaning step in order to have meaningful data to work on. And then we have the model training. Of course, we have the model definition, we have the definition of several experiments and all this stuff. We train the model, and we do also the model selection. So we choose the model that reaches the best performance on a specified metrics. For instance, we may be interested in the top accuracy or the best results on the area under curve and similar metrics. In the end, we reach the deploy phase. So in practice, the data gathering is done by any language, whatever. It's a machine, it's a sensor, is something that just acquire data and store it somewhere. Then often what happens is that for the data cleaning, the model training and the model selection, the only language that is used is Python. We all know the reason. Python is rich of libraries. We have PyTorch, we have TensorFlow, we have Pandas, we have NumPy, we have thousands of libraries, we have scikit-learn and whatever. We have thousands of very good libraries that allow us to just script solution and a working solution. So Python is really the good choice. But when we reach the final stage, so the model selection, and we just selected our best model, this is our boy. So what happens next? Next, if we reach the end of this pipeline, there is the deployment phase. The deployment phase is something that it's difficult. It's difficult because maybe you can't use Python. Maybe you are constrained by the environment. Maybe you have a limited resource devices. So it's not the easiest part. Here comes TensorFlow with its environment. So TensorFlow comes with separated environments for the training and for the deployment. As you can see, in Python, we can do all the training stuff. We can do the data processing, we can do the model training, we can do the model selection, we can choose any target device for doing the training, so we can train on CPU, GPU, on the TPUs for having the best performance. And after that, before the deployment, we must export our selected model in this format that is called SavedModel. The SavedModel, as you can see from this diagram, is the only entry point or the only connection point that we have between training and deployment. After that, with a single SavedModel, we have multiple deployment platforms. For example, a SavedModel can be deployed using TensorFlow Serving, so on a cloud, on TensorFlow Lite, for instance, on a Raspberry Pi, on a mobile application, even in the browser. And as you can see, we have other language bindings. Other language bindings, it's really interesting because it opens the possibility of deploying a SavedModel everywhere. And I say everywhere because the language bindings are built upon the TensorFlow C library. So you just need a device that it's able to run C programs. And maybe you can just have the compatibility with this C runtime and the other runtime. For instance, you want to deploy it in Java. Perfect. You just have to create the bindings for Java using the C API. And then you can use it inside your Java application, the model you just deployed it. So, in this talk, we are going to cover these two parts. So the first part is the SavedModel. We are going to see how to create a SavedModel and what are the correct rules to create a smart SavedModel, because we are not constrained only in exporting a SavedModel that is just a trained model, but we can export everywhere, but we'll see this later on. Not everywhere, but everything, and we will see this later on. And in the second part, we will see the other language bindings, and in particular, we will focus on Go. So we can start with the first part, the SavedModel. So a SavedModel, it's equal to a TensorFlow program. So this is a description that I quoted from the official documentation that it's worth reading. So a SavedModel contains a complete TensorFlow program, including weights and computation. It does not require the original model built-in code to run, which makes it useful for sharing or deploying. The most important part here, and the emphasis is mine, is the computation. So SavedModels are TensorFlow programs, and TensorFlow programs are just computation, a description of a computation. So, in fact, with a SavedModel, we can represent any sort of computation, and this is really powerful because we can write everything using Python, using TensorFlow in Python, and it's easy. We can define training loops, we can define iteration over datasets, we can define, we have also hash maps inside of the TensorFlow source code. We have almost a complete standard library and even more. And then the same code, the very same exact code can be executed by the TensorFlow C++ runtime by any deployment platform. Just think about this, and just think that if you have to rewrite everything you have done in Python with the target language. For instance, you have to rewrite with Java, with JavaScript, all the training phase, all the gradient computation, all that is needed for training or for fine-tuning the model. It would be painful. The SavedModels instead allow us to use a single runtime, that is the TensorFlow C++ runtime, and just having this abstract description of the computation executed. And this is great. This is really great, because of course, having the TensorFlow C++ runtime, we have all the optimizations that this runtime contains. So, for example, we have all the computations that are compatible with the GPU. So if our target device has an NVIDIA GPU, then this is perfect because all the operations we will use the CUDA backend. Our target machine have the vectorized extraction support. Perfect. Automatically are used. So this is really powerful. So the TensorFlow SavedModels are TensorFlow programs, and the TensorFlow programs are just description of the computation. So the description of the computation is the TF graph. And for being exported, the computation should be, of course, parsable. And there must be a well-defined order of execution. So it's easy. We just need to have a function that takes some input and have some output. And then the only thing we need to know is the name of the output. For example, in this graph, we can see that the output is the name G, and the input is just F. And so by using G and def, then we can trigger a computation. And for example, using this kind of data structure that is a data flow graph, and TF graphs are represented using data flow graphs, everything that can be executed in parallel, for example, the computation of G and H, is executed in parallel automatically. We don't have to worry about this kind of optimization. And in TensorFlow, using TensorFlow version 2, of course, don't use version 1. So using TensorFlow version 2 and later, we only have one single way of creating TF graphs. We have to use the TF function decorator. So, as you can see on the right of the slide, there is a simple function that is decorated with the TF function decorator. In practice, what happens inside this function? We have this if-elif, and it just uses only TensorFlow primitives. For instance, you don't use the greater, equal, less than operators proper of NumPy, but it's better to use the TensorFlow primitives, so you have to use tfmat greater, tfmat equal, and so on. Because what happens? It happens what is described on the left. So we have a function decorated with tm function, and on the first call, we have the parallel execution of the function, so it gets executed in Python. And in the meantime, we also have this module called autograph that tries to convert everything that it's been written inside pure Python into the TensorFlow equivalent. For instance, if the function contains the Python range keyword to iterate over a set of values, then this range is converted into a TensorFlow primitive operation that is tf.range. And so on. So the for loops become the tf while, the assert become the tf assert, and so on. But anyway, it is better to be explicit from the beginning. So it is better to already use the primitive operation. For example, on the function on the right, I could have write directly, for instance, a greater than b using the Python operator of greater than. But in order to simplify this conversion process, I highly recommend to always use TensorFlow primitives. Anyway, the function execution is traced. The autograph tried to convert what is possible to convert, and then this information is mixed together in order to create this TF graph. So we have created an operation. We have created a graph that has, for example, 2 input, and in this case have 0 output, but its computation has a well-defined order of execution. So, and it also prints something. Then what happens is that this graph, it's cached, of course, is added inside a cache. And this has been done because, as you may imagine, tracing, running autograph, storing, creating a graph is an expensive operation. And so it is just put inside a cache where the key is the function name concatenated with the arguments. For in this example, it's if underscore elif ab with the type of ab. And that's it. So we have created a graph and we stored it. Then on any non-first call, so on any other call of this function that is not the first one, then we have just the lookup inside the cache and we just gather the concrete function. The concrete function is just a way to call the TF graph. In practice, it's a callable wrapper built around the TF graph. But in practice, we can consider this concrete function as our TF graph. So the typical scenario. The typical scenario is the exporting only of the forward pass. So let's say we have a trained model. An example, we just download from the internet using Keras applications, the MobileNet network. And we just define, so we do the first call, the first invocation of our model in order to define a graph. So we, as you can see here, we have the invocation of this pre-trained model over a generic input X, and we have the output. This is required because, as explained in the previous slide, tracing the function execution is mandatory in order to create a graph. Now that we have a graph, we just have to invoke the tf SavedModel save to go from this Python representation, so the concrete function, to something stored on the disk. So in this example, we can save as a SavedModel the forward pass of a model, so the MobileNet forward pass, so just considering the model trained, give an input and expect an output, because a TF Keras model is a TF module. So we have this inheritance relationship between the TF Keras model and TF module. And moreover, in order to create a graph, we must have a TF function decoration. And the call method, so what happens when you call this object, is decorated with the TF function. So we create a graph. The important takeaway here is that every computation inside a TF module can be exported. Every kind of computation. And of course, every kind of computation must be wrapped inside a TF function decorated. So let's see if we can even export the training. So instead of exporting only the forward pass, we can try to export the whole training step. Because as we suggested, as we said previously, every computation inside the TF module can be exported. So let's start with this example that we also reuse later on in the presentation. So our goal is to classifying sensor data. So what we want to do here is just give a possible outcome. For example, here we say we have 6 available classes. So give a prediction over 6 classes for every x, y, z tuple that is given as input. So, for example, this might be the data that comes from an accelerometer that you might have on your smartphone or on any other fitness tracking application. So, we can define just our class, I named it custom, that inherits from TF-model, exactly like the Keras model. Then we can define some useful attributes, the number of features that we expect as input, and we use the same parameter in the input layer of this sequential model, and the number of classes. This is a really easy model. It's just an input, 32 neurons in a fully connected layers with a ReLU activation function, and then in output we just have the number of classes, so 6 neurons as output. We don't have an activation function here because we will use TensorFlow losses that automatically applies the activation function at the end. Then we can define the variables. We need to use variables that are graph convertible, so we will use TF variable, for instance, for the global step. So every training step we will increment this variable, starting from 0. And then we can define also the optimizer. The optimizer is the tool that we need to apply the gradients, so to do the optimization steps. So we can define the first function decorated with TF function. For example, here we just want to be able to export one training step. So the learn function just takes as input the sensor data and the label. Then we just increment by 1 the global step. So the global step variable is just incremented by 1 every time we invoke this function. And then we use the standard and also called custom way of training a model. So we define by ourselves the training step. So we created this object, the gradient tape, that just allows to track what happens inside this context. So we do the forward pass of the loss. So we do the forward pass of the loss between the labels and the model output, given this sensor data. And we also print the value of the loss. Then we compute using the tape the gradient, so the gradient of the loss with respect to the trainable variables. And then we use our optimizer to apply the gradient. So we perform the optimization step, and then we return the loss value. After that, we can define also the predict class, the predict method. The predict method is the method that we use during inference. So we don't have the label information. But what we need is just the model prediction. So we just do a forward pass. So we call the model with the sensor data. And then we just cast, we just use the argmax method to get the position of the neuron that has the highest probability. For example, if we have 6 neurons and these 6 neurons, the first one is the class walking, the second one is the class resting, the third one is the class jogging, and so on. It gives us the index of this neuron. For example, given an input, we have the output that is running. And then we return the predicted position. So we have defined our custom model. We can just initialize it, so we just build the object custom, and then we must do some dummy forward pass. So because as explained in the beginning, what we need to do is to create the graphs before being able to save them. So we just do a dummy forward, a dummy invocation of the learn method, passing some zero value as sensor data and some zero value as label. And we do the same for the predict. In this way, we have created and put inside the cache this concrete function and those our TF graphs. And then using tf SavedModel.save, we can save our model with a name, we name it custom, and that have certain signatures. The signatures are elements, functions inside the saved model. So we have the learn signature that is mapped with the custom.learn method, as well for the predict. Please note that we only described the computation, and we already have a saved model ready for the deployment stage. So we just describe it. We don't have run any training step. We basically just describe it, what we expect that a training step will do and what we expect that predict step will do. And that's it. As you can see on the right, this is the output. So we have the saved model that is just a folder. This is a folder with a folder inside that is assets, because we can ship some metadata information with the saved model, but we didn't this time. We have the saved model that is the description of the computation. It is portable representation, so as a protobuf. And then we have a folder variables that contains the value of the variables. In this case, since this is a dummy model, we just have the variables with some random value. So this is not a training model, but of course we have variables initialized and are with a specific value depending on the, of the default initializer strategy of the dense layer that we have in our model. Okay, so now that we have a saved model, what we can do is to use it. It's to use it for doing the training. And we can do this using Go. So in this part of the talk, I'm going to explain to you what are the advantages and how to use the TensorFlow Go bindings and what are especially the cons. And then I'll show to you the tfgo package I maintain. That is better. So, TensorFlow Go bindings. So these are the steps that are required to create a language binding for TensorFlow and for any other library that has a C API. So in practice, we need to read this list carefully. So cgo, that is the Go C foreign function interface, allows us to call C from Go. That's great. So we have one step of compatibility. TensorFlow has a C API. Perfect. We have two steps of compatibility. Moreover, TensorFlow is a pre-built C library that comes also with or without GPU support. We can decide to download from the TensorFlow website the C library with the headers and whatever, the C library that pre-built for Linux with and also macOS with and without GPU support. Moreover, TensorFlow is a Go API that is already built around the C API, so we don't have to write C. And there is a Go gettable package, so we can just go to go get it. Okay, the things we need to do are install the C library in the system, because of course it is required during the linking phase. We need to create a new project using Go mod init, and then we have to go get the TensorFlow Go package. And as you can see, what we have, it's an amazing error. And this is unsolved by, I guess, almost 1 year, or even more than 1 year. So currently, the official TensorFlow Go package is not go-gettable. You have this problem, for instance, is something related to some protobuf that is not available while you go get the TensorFlow package, and that you need to fix this manually somehow. However, I have created a fix for this. So instead of getting the official TensorFlow repository, we need to get the fork I created, so you can find it on my GitHub. And specifically, we are interested in tailoring the last TensorFlow version, so release 2.4. So I created this branch, so R 2.4 minus go. And we can just go get it. We can go get it and it just works. For instance, we can just try to run the tests. As you can see, all it's green. Yes. Okay. So we can see how to use the Go bindings. So for using the Go bindings, we need some boring stuff to do. So of course we need to import the Go package that we call it TF using an alias. And then we also need to import the op package. This op package contains the basic TensorFlow operations, and it also contains the concept of scope. The scope, it might be seen as the root of the graph. So, for instance, just for running a simple hello world, what we need to do is create a new scope, add an operation. So an operation is a node in the graph. So we add this constant node to our graph S. That is just the constant string hello from TensorFlow version, TF version, that returns the compiled the version of the compiled library. Then we need to finalize the graph, because it's the same as describing the computation using Python. So first we describe and then we finalize. So we created from the description a graph. Then this is familiar to the people that already have used TensorFlow in the version 1. Whatever, because now that we have a graph, we must execute the graph inside a session. So we need to create a session and give to this section a graph. In practice, creating a session means allocate somewhere. So if there is the support for the GPU on the GPU, if there isn't on the memory on the host memory, whatever. So just create, allocate the space and place it the graph, so the computation in that location. Now that we have allocated the memory and placed everything inside, and moreover there are also some other kind of check that everything is constant, that the graph works correctly and so on. But once we have placed the graph on a device, we can run it. So we have to specify what is the node that we want to fetch. For example, here in this case, we need to specify that we want to fetch the output from the node C. And then we have to execute it. Once we have executed, we have to extract the value. So as you can see, to pass the output nodes, we just need to declare a slice of TF output with all the nodes we want to fetch. Then the output will be a slice as well, and we need to get the first value. So for example here, output in 0 and get the value using the value method. So the output is hello from TensorFlow version 2.4.0. Okay, so for writing an hello world, we need to have a lot of concepts in our mind. We need to know how to describe, we need to know where to get the operations, we need to know a lot of steps. But at least it works. Okay. And this is instead how to use the Go bindings in a simplified way. So instead of using the TensorFlow official bindings that are broken, so you have to use my fork. So instead of using the official TensorFlow bindings, it is better, I highly recommend to use tfgo. tfgo is a simplified interface for the Go bindings. I defined it, I guess, almost 3 years ago, and it's still working, so yoo-hoo. So in practice, instead of creating scopes, instead of creating a graph with that horrible syntax in this way, we can just use method chaining for create and concatenate the various nodes, because it's natural. It's really, really natural using method chaining to connect different nodes. So for example, we can just use tfgo and create a new root. So this is exactly the root of our graph. Then we want to do a matrix multiplication and an addition of a vector. So we define using the new tensor a new tensor that contains this data. So this is a matrix with the value 1, 2, minus 1, minus 2. Another vector that is the x vector that contains this data, and so on for b. And then we can have this small masterpiece here that it's just a. So the first matrix multiplication, so matmul, this is a method of this tensor, x output, so the value of x, and also add to this result the value of b. So using method chaining, we just described the whole graph. So what we need to note here is that why it's a pointer to a, because of course this is the result of method chaining, and with method chaining we just return a pointer to the self method, so the self instance. So if we want to create a different node in the graph, we need to clone y or equivalently a. So these are just some minor things to keep in mind. Then, always using tfgo, we have this exec method that allows us that given a graph, you just specify exactly like the session run in the standard API. You just specify the list of the output nodes you want to fetch, and then you fetch it. And these are pretty much the very same stuff that we do in the standard TensorFlow API. So this is the result. So we have the value of y, we have the expected result. So for instance, as we said, y is just a pointer to a, so these are equals. And then instead we cloned using the clone method a, so we created a complete different tensor, and this complete different tensor of course is not equal to a, and in y we have the value of our matrix multiplication and sum of b. So once we have introduced all these new concepts, we can go back to our example and just remember that we have defined the model that takes as input 3 values, so x, y, z, and gives in output, once it has been trained, the label for that set of values. So as an example, we are going to use the wireless sensor data mining dataset. That is a dataset that has been collected in this way. So as you can see in the video, some people in a laboratory just, and this is something old, I don't remember exactly the year of publication of this paper, but is something old. So they just mounted on this guy a device with an accelerometer and just have the values of these 3 components acquired at every second, or even more. So we will use this data, and this is, for example, a snippet of the dataset. We have the x, y, z values. We have a timestamp that we don't use in this example, and we have the label. Moreover, you also have the ID of the person that is executing the activity. So, since we have a SavedModel, what we can do from Go? In Go, we can read every word of the dataset. We can create batches for each user, because of course we don't want to mix information that are related to activities of different users. We can call the learn graph from the SavedModel, so we can train the model directly from Go. we can simulate, moreover, the real behavior. So when we have this deployed device, so we have some new data that arrives, for instance, and then we can call the predict. So we have trained the model, and then we receive from a channel, from whatever, some new data, and we want to classify this new data. Moreover, to complete the simulation, we can also add a step where we ask the user to validate or reject the prediction that our model has just executed for this new data. And if the law, just think how you can fine-tune and improve the result step by step, because if we have trained the model, we have deployed this model on a device. This device has a saved model. So we have deployed the saved model on this device, and we have the learn graph and the predict graph. We can use the predict graph to predict the label. And then we can ask the user, hey, is this label the correct one for the activity you just performed? And if the user say yes, okay, so we have the correct label and we have all the data. So we can do a training step and improve the quality of the model. Instead, if the user just said, no, I just was sleeping and you predicted that I was running, then the user can give the correct label for that kind of data, and we can do the step to correct the quality, to correct the prediction. So we can do a training step to correct the prediction and improve the quality of the model itself. Of course, using a fully connected layer is not the optimal solution. We don't take into account the temporal relationship, and a recurrent neural network would be a better solution for this kind of problem, but it's out of the scope of this talk, so this is just an example. Okay. Okay, so we can just have a look at some Go code. So we can start by defining some observation. The observation is just a row of our dataset. So we have the ID, the activity, the label, the timestamp, and the three values we want to create. Then we can define this new observation function that in a pure Go style, it's new type. It just instantiates this type. So we suppose that the input of this function is a slice of strings, and also we have the mapping between the textual representation and the numerical representation of the label. And we do some kind of parsing. We convert from string to integers. We find the activity. We have the conversion from this string to a float value in order to have the correct data types. And once we have done all of this processing, we can just return a pointer to our observation. Then we must convert the observation to a TF tensor, because TensorFlow only knows about tensors. So the only way we have to feed a model is to go from the Go data type to this TF tensor data type. For doing this, let's suppose we have the observations to tensor function that takes as input a batch. So a batch of observations, and give us an output, a pointer to a TF tensor. So what happens here is that we just do some check, because we need to have a batch size. All the batches must be equal. And then we just populate the sensor data using the observation. So we get rid of everything we don't need. So our TF tensor, we will just contain the X, Y, and Z components. A batch of X, Y, and Z components. And using the fork of TensorFlow, we can just create this new tensor and return it. Okay, so we have the observation and we have the conversion from observation to tensor. How can we use the SavedModel? So for using the SavedModel, we have to look inside the model that we exported previously. In order to inspect the SavedModel, there is a tool called SavedModel CLI that allows us from the CLI to inspect the content of a SavedModel. So we just need to invoke it with the show command and passing the parameters there, that is the directory of the SavedModel, and tag. Tag is basically just always serve, because SavedModel are designed for serving. And then we have the all, because we are interested in all the content of the SavedModel. And this is the output. So we have different signature depth. As you can remember from the export phase, we have defined two different signatures, and here we are. So we have the learn signature and the predict signature. In the learn signature, we have some named nodes. So we have the node that expects to have in input some label. We have the node for the sensor data, and we have some output node, the loss, that this name is stateful partitioned code because we haven't renamed it. And the same for predict. We have as input predict sensor data, and as output stateful partitioned call _1. So these are all the informations we need to have a function, learn, predict, the inputs and the output. So we can define the learn, the execution of the single training step from Go using the SavedModel. So we can define this function that accepts as input a TensorFlow, so a tfgo model, the sensor data is a tf tensor, and the same for the label. And we just exec. So we just ask to the SavedModel, so to the TensorFlow runtime, to use the learn sensor data, as you can see here from the tensor info, the input. We pass this tensor, the sensor data, the same for the label. And we ask to the SavedModel to get the value of the output tensor, that his name is stateful partitioned call. Since we defined the learn function to return a float value, that is the value of the loss, we can assign it. Then our function just extract from this tensor the value and do the casting to the correct value we expect, so the float 32. We can also define the public learn function that just converts all the observation we give to input, we give as input as a sensor, extract all the labels information that we need. We create a new tensor from the label, and then we invoke the private, so the private learn function. We can do the very same thing for the predict. So for the prediction, we just use the exec with the correct output, with the correct input, and we do the we do the type assertion for getting the correct values in our Go predictions variable. And then we just want to sort, so we want to give one single label for a batch of sensor data. So we just want to give the single label that our model predicted more often inside the batch. So we do this computation in order to return the top label, so the one most voted label. And we do the very same for the predict function as we did for the learn. Then we can train the model. So what we need to do is we have the train function, perfect. We have the new observation function, perfect. We can just use it. So we just have downloaded the dataset, and we can just invoke a new reader. This new reader is a CSV reader because the data is a CSV. And then we just read line by line. We create the observation. And then when the user changes, for example, because we want to have only data of the same user. So when the user changes or the label changes, so we are ready, once we have gathered enough data, to invoke the learn method. The learn method takes the model as input, and also the batch of the observations that we have inside that we have just gathered. Of course, inside the observation there are the labels, so we have everything we need to execute a training step. So given the mapping, for example, we have the walking, jogging, upstairs, downstairs, sitting and standing. We have the tfgo model, and we just need to load it. So with tfgo, we can just load a saved model, giving the path. So it's in the current working directory. We have the custom saved model we exported. As I said, we need to specify the tag that it's almost always serve. And then we can invoke the train function, given the path of the dataset. And as you can see here, this is a snippet. Just note that we don't have any single print statement inside the Go code, but we have an output. The output, it's all executed by TensorFlow runtime. So the output, as you can see here, is the loss value. So we have changing labels, and this is something that we did in Python. So we have described it inside of the graph, so we have it also here. And then we have step by step the value, the loss that is decreasing. And this means that we are applying several optimization steps. So it is working. We are training a model from Go, and this model is just been described from Python. That's it. So we reached the last part of the presentation, where we just simulate the incremental learning using channels. So it's just a simulation, so nothing really useful, but it's to give an idea. So we can just create a channel of observations and a channel of predictions, and the usual, a very common done channel that just becomes 1 or 0 when data is ready. And then what we have, we have a routine, so a Go function that just waits over the prediction for new data. So we just read from the observations channel as soon as they are ready, new observations. Once we read enough data, so batch size, we do the prediction step using the saved model, and we send the prediction through the channel. This is something that we don't need right now to understand. And then we have another function that is just the simulation of our sensor. So we just simulate some random values for the XYZ components, but this might come from the real Rife device. And then we have the predicted label that just read from the channel prediction. And then we have just made a supposition. So we have supposed that the predicted label has been confirmed by the user. And so we can have all the observation read again from the channel. So we have requeued here in order to do this here, where we assign the predicted label to every label, to every observation that has been generated by this routine. And then we do a learn step. So we have just executed a prediction, have the user that confirmed the prediction, and then we executed a training step using the model given this batch of observation. And then we have the final part. So we have the, okay, we want to close the application. So we send the done, the Boolean value of the done channel, and then we close the application. So we reached the end of this presentation, and these are the main takeaways. So a saved model is a TensorFlow program, and we can describe any computation using TensorFlow primitives. The computation can be exported as a TF graph only using TF function. The signature should be specified while decorating the method of the TF model, of course. And cgo, that is the Go C foreign function interface, allow us to call C from Go. We have the C API. Don't use it, the official Go bindings, but use tfgo and my fork of TensorFlow, because it's are the only one that just works. And if you are interested, there is on my personal blog a more detailed description about this use case. So I guess this is everything, and thank you very much for your attention.
Thank you so much, Paolo, for a very interesting talk. Now we have some time for your questions. If you have any questions to ask Paolo, please write them in the Q&A chat and we can go through them. If anybody wants to ask anything. Otherwise, of course, you can ask questions about any of our talks to our Discord channel.
Okay, so maybe I'm reading on the Discord channel itself. There is a question, and maybe I can read it. So the question is if there are some example of unit tests and training function or similar inside the project tfgo. So for answering this question, yes, there is something that there is very small. So there is some simple use case with just a training in Python and the running the inference from Go, and there isn't everything that I presented in today's talk. For finding a complete example of how to use Go for training a model, you have to. For the only example you can find is the blog post that you can find on my blog. And you have to, I guess, scroll a little bit because the latest articles are about Bazel and other TensorFlow related stuff, but not about this topic. Anyway, to answer your question, it's not inside the official tfgo documentation, but it's inside the blog post.
Can tfgo be used to solve NLP problems?
Okay, so for solving NLP problems, perhaps if you want to follow a pure Go-based approach, you have to use another library, perhaps SPA-Go, so SPA-Go. It's a library that it is a pure Go, and you can just define everything and solve your problems directly in Go. Instead, if you wanted to use tfgo, your only option is to write, as I showed in this presentation, everything in Python and then export it. Or better, if you just want to run the inference, this is something you can do. Instead, if you want to develop something that is an NLP-based solution with dynamic elements, better. If you wanted to develop something that is an NLP solution, but it is something static, but for instance, you just want to do some kind of pre-processing to your model, then using tfgo, you can execute pre-processing in an optimized way. Because with all the wrappers that there are in the SIGO library, you can execute you can define a static graph that executes the pre-processing of your input and then feed the model. This is the only thing you can do with tfgo. But perhaps this is not the optimal solution because NLP is way more flexible and tfgo has been designed for solving the problem of the inference and for doing computer vision tasks. Because currently right now there is only the image sub-package inside tfgo that contains some utility function for doing computer vision using Go, but there isn't a specified model for NLP.
And we have another question by user Simone. Is there a significant performance difference from Python and Go in everyday uses using TensorFlow?
Oh, well, it's completely different because, of course, with for the point of view of the performance, we have the problem of SIGO. Because with the SIGO, we have to switch from the Go runtime to the C runtime, and so we have to pause all the garbage collection and everything, all the Go routines and all the stuff that are working in Go, throw it away and start a new runtime, execute these things in the new runtime, so the TensorFlow runtime, and then restore the status of the Go runtime. So all these context switches are a waste in performance, and the performance can only increase if the quality of SIGO increase over the time. But this is not something that we can solve by ourselves. We only have to hope in the Go developers, in the designer of the language, in the developers that are working on the C Go for improving this switch.
Okay, it looks like there are no more questions. And so, as other announcements, we can say that all our sessions will be available on YouTube on the GoLab channel. So go and subscribe to the GoLab channel. And you can find the next events on the website golab.io. And to remain up to date on upcoming events, please subscribe to our newsletter. You can find the information on how to subscribe in the notes. So, thank you very much, and we hope you enjoyed the talk, and we hope to see you again for our next events. Goodbye.
Thank you very much. Goodbye, everyone.